Ananya, can you hear me?
Yes, sir.
Okay, all right. So, do we remember things that we did in the last class? Ananya, did you have the time to go through these things? Maybe.
Yes, sir. I went through them. Something.
Okay, and is there any doubt?
Yes.
Okay. How about you, buddy? Did you have time to go through things? And did you understand it when you went through it? Okay. Yeah. Yeah. Tell me.
I got the book history, but I'm not sure which chapter it is from.
Okay. So the chapter, I think it's chapter number 12. No, 11. 11.
Which chapter?
Chapter number 11. Not 11. 1 minute. Let me just check. It is. Yeah, chapter number 12. 12. It's thermodynamics. Thermodynamics, chapter number 12 in the second booklet. Okay. All right. So, 1 minute. Are we. Not 12, sorry. We are doing chapter number 11. We are starting from 11 and then we. Yeah, chapter number 11. It's thermal properties of matter. That's the one we are doing right now. Okay. Did you find it? Yeah, okay. All right. Fine. So the thing is, see, your 11th syllabus, no, it's quite extensive. As in 1 hour or 1.5 hours, we can cover a lot of different things. So you have to try to keep reading after every class. Otherwise, in the next class, you will be clueless. And as easy as it is to understand, it's also easy to forget. Okay, I'll turn off this fan in the front. Okay, yeah. So now, what was the last thing we discussed? What was the last thing we discussed? Coefficients of expansion, correct. And do you remember what is a coefficient of expansion? What is the meaning of it? Correct. So coefficient of expansion, basically what it tells us is, it gives us an idea of how much any particular material will expand for a certain increase in temperature, okay, or certain decrease in temperature, it will compress. So how much is that going to happen? Not all materials will expand in the same way. Water will expand, maybe if you give, you know, raise the temperature by 50 degrees, water might expand a lot. But it may not be the same case with steel. With steel, if I want to see the same kind of expansion, I may have to increase the temperature by, few hundreds of degrees. Okay. So not all materials behave the same way with respect to heat. They do not respond in the same way. And therefore, we have this value called coefficient of expansion, which tells us how much a particular material expands. Okay. So we discussed that the coefficient of linear expansion is given by alpha. The coefficient of superficial expansion, or a two-dimensional, and alpha corresponds to one-dimensional expansion, meaning this is the expansion in length, breadth, only one dimension. Okay. If we have a wire, it will expand in length. So we are only talking about one-dimensional expansion. Now beta is superficial expansion, so it is the expansion in two dimensions, as in it's not only length but length and breadth, the area of the thing is increasing. And the third one we have is gamma, which is cubical expansion. So this is a three-dimensional expansion, the volume is increasing. Okay. And there is a particular relation between the three of these things, that is alpha is equal to beta by 2 and this value is equal to gamma by 3. Quite simple. alpha by 1 you can say, which stands for 1 dimension, which is nothing but alpha, is equal to beta by 2 because 2 dimensions, and is equal to gamma by 3 because 3 dimensions. Okay, quite simple. Now there is some now when we talk about water though has a very strange behavior. Okay, now we remember, if we look back and remember what we did in last class, we talked about something called the Charles law, right? And what this guy found was that at constant pressure, what volume is directly proportional to temperature. Okay, so if I increase, so ideally what this means is that if I take a graph, let's say I take some material, I take some oil, let's say, and slowly I'm increasing the temperature. Okay, so first I will keep the temperature, let's say 10 degrees Celsius, and I see the volume, it is some particular value. Okay, so I find it. Okay, after some time I increase the temperature more, the temperature has gone to 20 degrees Celsius. So even here, and then I measure what is the volume on this axis and I plot it, it will be this much. After, let's say, some time again I increase the temperature more and it becomes 30 degrees Celsius, and I check the volume, I will find that the volume will lie somewhere out here, meaning that the expansion is linear. It is please excuse this drawing. So when I connect the lines, it is going to be a straight line. Okay, so this is the meaning of directly proportional. As this is increasing, in the same way this is also increasing, or vice versa. But the strange thing is, water has something called anomalous behavior. Okay, and the problem here is, if I take some water and I start increasing the temperature, okay, some strange thing happens from 0 to 4 degrees Celsius. Okay, it is a very strange behavior. Ideally, see, according to what we see in the left hand side, V versus T graph, it should increase. According to Charles law, it should go straight. But what we see is that the volume initially, it decreases till 4 degrees Celsius, and after 4 degrees Celsius there is an increase. Okay, so what is happening is, from 0 to 4 degrees Celsius the volume is decreasing, means the density is becoming more. Volume is decreasing, it is becoming more dense. So ice is there, no, ice is not melting, ice is becoming more compressed till 4 degrees Celsius. And this is a very interesting thing, because you must have seen in very cold countries, on a lake, or if you put some water in a fridge, in a bowl, you'll see that the top layer is ice, the bottom layer is water. So it is only the top layer which is ice and the bottom layer becomes water, and this is good for the fishes because they can swim and all of that. This top layer, it protects them. Okay, so that is what will happen. Till 4 degrees Celsius, instead of melting, it becomes more dense, and after that the process of melting kind of starts. Okay, yeah. So what we can do is we will look into discussing another particular topic, a very interesting topic, which is called specific heat capacity. Okay, specific heat capacity. So the thing is this. Okay, now if I have any kind of a material, I have to describe its properties, correct? Now for example, if there is a human being, for describing the properties of human being, there are different types of properties. For example, if the person, you want to describe his smartness, what you will tell? You will tell that his IQ is so much. If the person is fit, what you will tell? You want to measure the fitness, you can talk about maybe weight, you can talk about the height, you can talk about he is athletic or not. If the person is very Emotionally strong, you will say what? Maybe you will say that he is very perseverance, he is working hard, he is hardworking, he is emotionally stable, things like that. So the thing is, even one person, no, he has different types of properties. You getting it? Now there's a smartness type of a properties there, for which you'll measure it using IQ. Maybe if you want to measure his physical property, you'll talk about weight, height. They are different properties, but they are talking about different aspect of a person. Okay. Similarly, if you want to talk about a material, there are different types of properties. And in now there are different properties, physical property, what is its height, what is its weight again. But that is not what I am interested in here. I want to know about the thermal properties of the material. That means how it is responding to change in temperature, or how it is responding thermodynamically with temperature and all of that, how are its variations, how it responds. So that is where we get this idea of specific heat capacity. Okay. And see, firstly, there is something called heat capacity, which gives us the change in the temperature of the substance when certain quantity of heat is absorbed or rejected. See, if I have some, see, again, all materials will not behave the same way. If I take some water, if I take some oil, maybe for water I have to give a lot of heat in order for its temperature to change. Just because it's giving a lot of heat does not mean its temperature is increased. Okay. For oil, I might have to put it in one pan for 10 minutes for it to heat and its temperature to increase. For water, I may keep for 5 minutes only. It will heat to that temperature. Okay. So the thing is that each of these materials, they are taking different amount of heat to increase the temperature by same level. Okay. Water may increase by 4 degrees by taking little amount of heat. Oil will take a lot of heat to increase by 4 degrees. Getting it? This is the difference. So heat capacity, firstly you talk about heat capacity. It is given by S, which is delta Q by delta T is equal to MC. Delta Q is nothing but the rate of change of heat, how much heat we are giving. Okay, I may give, let's say 5 joules of energy or something like that. Okay, it can be any kind of heat. Delta T is how much temperature. That's all. That is the ratio of that. And this is equal to M into C. Bhaskar, can you turn on the AC? Is okay, fine. M is nothing but our mass, okay, and C is something called specific heat. I don't think so. Only that recording mobile you gave me. Yeah. And C is called specific heat. Okay. This is called specific heat. See, the thing is, you guys will have to read a lot and you will have to understand these things again and again. Otherwise, it's very easy to confuse them. It's very easy to get confused, to forget. Okay, specific heat is a quantity. It is a particular value for a particular material. Okay. So now see, water, air or something. How will this equation know if it is water or air? It won't know. So what do you have to put? You have to put the value of C. C is one particular value. Every material will have one values of specific heat. Okay. So that's how you'll get to know. The equation will tell you. Okay. Now specific heat capacity, which is this value, that is what we are going to define. Okay. It is given by same what did we write in the previous equation? Maybe you can note this down. See, we wrote delta Q by delta T is equal to MC. So how am I going to define C? C will be nothing but S by M, or it will be delta Q by M delta T. Simple, no? It's very direct. So this is our specific heat capacity. Now, how do I define this specific heat capacity? Okay, it is the amount of heat that is required to raise the temperature of 1 unit mass of a substance by 1 unit degree. Okay, what is specific heat capacity? I'll write it here, specific heat. Okay, you want to note this down? Okay, you can note this down. It is the amount of heat, note this down, specific heat capacity. It is the amount of heat required to increase the temperature of unit mass of a substance. It is the amount of heat required to increase the temperature of unit mass of a substance by 1 degree. Okay. Okay, is this clear? And its SI unit is joule per kg Kelvin. Joule is what? Amount of heat. Per what? Kg. That means amount of per unit mass. Kelvin means what? Temperature. Okay, same thing. To raise the temperature by 1 degree. Is that clear? The unit will always help you remember the definition, or the definition will always help you remember the unit. Okay, joule is the SI unit, the joule is the SI unit of our what? Energy or heat. That's what we're using it here. Kg gives us the mass, Kelvin gives us the temperature. Okay, now there are a couple of types of heat capacities. The only difference is C. Here C was given by what? Q by m delta T, right? But instead, if I multiply this with the molar mass, this will be called molar specific heat capacity. Okay, that's all. If I multiply it into molar mass, and it's given by mc. Okay, now for a gas, for any kind of a gas, there are two types of specific heat. One is given by Cv, another one is given by Cp. Okay, so Cv, drink. Cv is the specific heat at constant volume. That's all. Okay. Cp, this is happening at constant pressure. So at constant volume, what is happening? Pressure is changing. At constant pressure, volume is changing. That's all. Okay. So how do we define Cv? The amount of heat, same thing. The definition is same. The amount of heat required to raise the temperature of 1 unit mass of gas. See, this is for gas, right? So the amount of heat required to raise the temperature of 1 unit mass of a gas by 1 degree when the volume of the gas is kept constant. So that much you have to add, that's all. Then what will be our Cp? The amount of heat required to raise the temperature of one unit of a gas by 1 degree when the pressure is kept constant. That's all. And the interesting thing is, for any given and if you want to again know the molar specific heat at constant pressure, you just multiply it by molar mass. That's all. So Cp, if I multiply this into m, and this is what Cv, I multiply this into m, that is our molar mass, we'll get the molar specific heat at constant pressure. This here we get the molar specific heat at constant volume. Okay, that's all. And the interesting thing about these two values is, if I take the ratio of Cp by Cv, it will be a constant, and this constant is given by gamma. Okay, maybe you can note this down. And the interesting thing again is, if I subtract Cp from Cv, I get this value called R. And do you remember what this R is? We discussed this in the last class. Does it look familiar? Yes, it is the universal gas constant. Okay, so these are some very interesting things. Okay, so math is all, again, what we discussed last class, it is agreeing with one another. We are discussing new concept, but it is still agreeing with the old concept. We saw last class how all these three scientists, Boyle, Charles, and all of that, during 3 different times of their life, from 3 different countries, they come up with 3 different results, and all of them agreed with one another, those results. So that is what science does. Okay, yeah. So there is also something very interesting. What they did was, they described something called water equivalent. Okay, so basically what they did was, instead of saying specific heat capacity of any material, I can describe it in terms of water. They said, how much the idea is basically this, that if I take some, now there is oil, okay, or if I have steel, let's say, it has one specific heat capacity, meaning I have to give so much heat to increase its temperature by 1 degree Celsius. Okay, so they said, in terms of water, what will be this value? How much water will I have to heat to get the same kind of a result? So it is just converting in terms of water. Okay, it is just a small thing, you can just look into it, or it's there in a textbook. It's just 1 sentence is written about it. It's not that important, I believe. Okay, how much water would be required to show the same kind of result, heating. Okay, if you take little water, it will heat very fast. If you take 1 bucket of water, it will take a lot of time to heat. So same kind of a result I want to show it in water. Steel will take 5 minutes to heat. Okay, how much water should I take to heat so that it heats in a similar way, and it takes 5 minutes. That is what they are doing. That's called water equivalent. Okay, fine. So now we are going to look at something interesting. We are going to look at something called calorimetry. Okay, calorimetry is basically a branch of physics which deals with the measurement of heat. So what we are doing here, we are measuring heat. Okay, this is our calorimetry, and any device which can measure this heat is called a calorimeter. That's all. Okay, so the idea here is very simple. The idea is this: if I have one body which is hot and another body, let's say they are at 2 different temperatures. That is a better way to describe this. This is at T1, this is at T2, and I am mixing these both. Okay, I am mixing, both are being mixed with one another. So the idea is, it says that the amount of heat, let's say T1 is hotter than T2, okay? Hot, cold. So this says that the amount of heat which is lost by T1 is equal to the amount of heat which is gained by T2. That's all. So whatever heat this guy is losing when both are mixing, heat lost is equal to heat gained. That's all. Obviously, if you are mixing two liquids which are at two different temperature, when one hot liquid will become cold, obviously the cold liquid will also become hot by the same temperature. How much one is losing, the other one is gaining. Is there any doubt about that? Okay. What about you, Ananya? Hello?
Yes, yeah.
You understood?
Yeah.
Okay, let me repeat this again. Let us take one example. I have with me one bottle, okay, or here I have water. It is at 50 degrees Celsius, okay, or here I have another bottle. Tell me some other liquid, man. I don't want to keep it water. Coke. Coca-Cola. Okay. This is at 30 degrees. Let's keep that 20 degrees Celsius. Okay. Or actually, for the sake of mathematics, 10 degrees Celsius. Okay. So which one is colder here? Coca-Cola is colder. Water is hotter. So now I take one vessel, empty vessel, and I am mixing this Coca-Cola also here, and I am mixing water here. So my mixture will be water plus Coca-Cola. Okay. What will be the temperature of this mixture? It will get neutral, correct. So it will be in between. It will not be 50 also, it will not be 10. It will be, let's say, exactly middle. It is in 30 degrees. Yeah. Yeah, it's 30 degrees centigrade. Okay. It falls exactly in middle. So what is happening to water are here? Water was before, it was at 50 degrees, but now water is at 30 degrees. So water has cooled down. What happened to Coca-Cola? It was at 10 degrees. Now it has 30 degrees. So as Coca-Cola heated up, it has heated up. So that is basically the idea. How much temperature water has lost? 20. So it has lost 20 degrees. How much has Coca-Cola gained? 20 degrees. So clear? The idea is the amount of heat which is lost by water is equal to the amount of heat which is gained by Coca-Cola. Both are losing and gaining the same amount. Okay? And both are coming to one middle point. Water is losing the temperature, Coca-Cola is gaining the temperature. This is not more than water, this is not less than Coca-Cola. It's in middle value. Correct? Okay, so this is it. This is the principle of calorimetry. Okay, and if you want to do this in mathematics, and if you want to write the equations, it is given by the heat that is lost is given by Q always. Okay, heat is equal to final temperature Q2 or theta 2, it's called, doesn't matter, theta 2 minus theta 1. Wait, let me write this again. Theta 2 minus theta 1. Okay, it cannot be very direct. So, but there has to be some, what you have to put the values of which values, specific heat capacity, mass, some things you have to put, right? because it cannot be directly the same. So it will be m into C. That's all. M is what? Our mass. This will be our specific heat capacity. Okay, that's all. Okay, fine. So, or here, if you want to write in a very fancy way, let's say call this temperature high, temperature low, and we'll call this temperature. Then what? Temperature high is greater than T, greater than temperature low. That's all. Okay, that's one way of explaining it nicely, putting it in words. Okay, so using this equation, some problems have been solved, and you can also do that. In fact, you know what? Let us solve one problem. Okay, you can note this down. Okay, Ananya, can you note this down? Have you written the equations, Ananya? Huh? You didn't write it. Okay. This is our equation. MC. This one? This one? This is not very required. Okay, you can note it down. It's not going to come anywhere. Okay, it is just for your reference, but it's there in the textbook also. Specific heat capacity at constant pressure is Cp, at constant volume is Cv. Okay. See, your Coca-Cola is there, no? Coca-Cola. When you buy a new pack, what is there inside? Pressure is there. That's why sound comes out. Correct? And once the pressure is gone, its behavior is different. The fizz, do you feel the fizz like before? No. Fizz is gone. After you shake too much and you open it, after 2-3 days, the gas is gone. The taste will change. So the thing is, the idea is the same. If you maintain the constant volume, no, its behavior is in one way. If you maintain constant pressure, its behavior is another way. Okay, that's all. And this value is the same for one material. If I tell Cp of water, it will be the same everywhere. If I tell Cv of water also, it will be the same anywhere. If I go to USA or if I go to Iran or Syria, wherever in the world, the water, its value, any one material, its value will be the constant. It is a constant material property. Okay. So I'll tell you the question and you can note it down. Okay. So the temperature of a silver bar the temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.23 into 10 to the power 3 joules J of energy by heat. Okay, the temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.23 into 10 to the power 3, meaning 1230 joules of energy by heat. The mass of bar is 525 gram. The mass of bar is 525 gram. Determine the specific heat capacity of silver. Okay, it's a rather straightforward question. Everything is given to you. Okay, so can we look at what is given to us? Ananya, can you tell me what's given to us? Have you noted down the question?
No, what is
What?
the voice is very low.
Can you hear me now? Can you hear me?
So can you get the mic closer to your
Yeah, I am doing that. Can you hear me now?
yeah, now
Okay. Fine. Were you able to hear the question that I said?
no actually
Okay. Maybe I'll just note it down then. Okay. But were you able to follow the previous discussions? Were you able to write down the equation and all?
I want the equation to specific.
Yeah. Did you write this one? This particular equation? Q is equal to this one you wrote, right? Okay, fine. So the question is this, okay? Just note it down. Maybe I'll write this down, and you start solving. Okay. Uh, Temperature of silver bar rises by 10 degrees Celsius. 10 degrees Celsius when it absorbs 1.23 into the power 3 joules of energy by heat. The mass of, just note this down, okay, Ananya? I'm writing this for you. Determine specific heat capacity, last one. Are you able to solve this? Yes, correct. Okay, so theta 1 and theta 2 is your final and initial temperature. So, do you know your final and initial temperature here?
Final is 10.
No, it says it is. Hello, yeah, can you hear me? Okay, yeah, so just note down this question. Okay, determine specific heat capacity is what is written. Okay, last part. Let me know, Ananya, when you have written it down.
So after finish, I send the answer to chat.
Okay, fine. But did you note it down? Because I will try to solve it, or I will try to tell it to you guys. So I can change the slide, no?
Yeah.
Okay. Yeah. So your theta 2 is final temperature, theta 1 is initial temperature. Okay. Or you can write it as T2 minus T1 also, it's the same thing. But in the question you are given, what is the first line?
Temperature of a silver bar rises by
The temperature rises by, means it is rising by 10, means maybe it was 5 and it 15. So the final and minus initial is 10. So you already know this value.
Oh. Then how does it?
That is your the amount of heat which is given, heat absorbed. Q is heat. Ten mass So you have to find C. Okay. So we have the heat given, we have M, we have C into theta 2 minus theta 1, which is nothing but final temperature minus initial temperature. Okay. Now we already know that the rate of change or by how much the temperature is changing is 10 degrees. Okay, and the mass is also given. So the mass is 525 gram into C into 10. Q, we know the amount of heat which is given, it absorbs 1.23 10 to the power 3. Okay, so all I have to do is substitute and find C, which you will get around 234. Okay, joule per kg Celsius, or kg Kelvin also you can write, because it's using delta T. Okay. Yeah, you have added 1 0 extra out there. See, 10,000. It's not 10,000. It's 1,000. Yeah. Yes. Correct. The easiest way to do this is first divide both by 5. Oh, you cancel the zeros. I think 121 is a. Okay. Can you do this later on? Okay. But you have got to know how to do it, right? The remaining is your mathematical skills. Okay. Alright. Now I'll tell you. Let's see how much time we have. Accordingly, let's see. Okay. I'll tell you one more question, and okay, then we'll move ahead. Okay. Ananya, are you clear with this?
Yes, sir, I got that.
Oh, okay, good. Okay, so we'll do one more question. You can note it down with me. Steam at 100 degrees Celsius. Or you know what, we'll do this some other time, I think. Yeah, it's better we do this the next time, because there are some concepts that we would like to clear, and you can go through it later on. Okay, that then it will make more sense. And maybe what we can do is I can ask you to study these things and come, and then we'll go for some slightly more difficult problems, so that those concepts will be in your head and it will be easier for you to understand. Right now, I think if I do them, you will just get confused. So we'll go ahead with the theory. Okay. Yeah. So now we will discuss the concept of change of state. Okay. Change of state. What is the change of state, man? Change of state. Something is changing. What? Correct. Yes. So change of state is quite simple. Everybody knows about this. There are 4 processes. One is melting. What is melting? When heat is applied, solid will become liquid. That's all. Okay. Okay. But an additional thing about this is, so there is one particular temperature. At that time, no, water will also be there, ice will also be there. Okay, you know, it is both are there. That point of temperature is called melting point. Okay, or here we say that water and ice are in thermal equilibrium, means both of their temperature is same. Water and ice, both their temperature is same at that point. Both are existing, their temperature is same, but their state may be different. It is ice, it is water. Okay, that's why it's called thermal equilibrium. Okay, and that point is called melting point. Quite simple. Next one is freezing. What is freezing? When you give heat, heat is not given. When you give cold, but you cannot give cold. You can, heat is released. Okay, when heat is released, liquid will turn into solid. Okay, so this is called freezing. That's all. freezing. There is no freezing point. Okay. Next one is condensation. Do we know what this is? When vapor is cooled, it will become liquid. That's all. Okay, water vapor will become liquid. You can note this down if you want, or it's quite straightforward. Okay. Next one is evaporation. What is evaporation? Heat, correct. And then what will happen? Liquid will turn into gas, correct. And again, just like melting point, there is one boiling point. It comes under this one only, okay? Evaporation, boiling point. So here what will happen at boiling point? There is a thermal equilibrium in which liquid and gas will both exist in the same temperature. This temperature is called boiling point. Okay, is this clear? Okay, there is one more very strange process. Do you know about this? Yes. Solid will turn into vapor. That's all. Here what will happen? Solid turns into vapor. Hmm? No. 1 minute. In the presence of heat is gone. Okay. What did you say? Ice turn directly into gas? No. It is the property of a particular material. Not all materials do that. Only some do that. For example, you know that camphor balls in your house? It is a solid which turns into vapor directly. Okay. In the presence of heat, that happens. Wax will melt. Wax kind of melts, but there are also waxes which directly turn into water vapor. Okay. They skip the whole melting situation. The liquid phase is only not there. Okay, that is called sublimation. And this happens, you know, when the boiling point is less than the melting point. Before it can melt, it boils. It's such a sensitive material that it boils at a very low temperature. Before it can melt only, it is boiling already. That's why solid to direct gas. Okay. Okay. Fine. And there are situations where you can take some water and it can directly turn into gas if the pressure is very, very low. Okay. Fine. Okay, fine. So now we'll talk about something called the heating curve, which is quite, it's as we see it is, you know, it's very simple. Heating curve is nothing but on one axis we have the temperature, on the other axis we have the time. Okay. So what will happen? First I take some solid and I keep heating it till time T1. Okay. But what will happen? The temperature of that will increase. Here it is solid. Okay. Till temperature, I'll call this chota t, I'll call this capital T, T1. Okay. From here, what will happen? It is melting. Ice will melt, right? But at this point, will it directly turn into water? Ice and water? All the ice will turn into water? No. There will be a time where ice and water will coexist. Some will become water, some will be ice. It is 50-50%, kind of like it is changing. Okay, it is transition. It is not completely changed yet. This process is called melting. And till melting happens, no, the temperature remains constant. Till this time will pass, but time is going on. But the melting, the temperature is not increased. This point is called melting point. Okay. Again, I'm going to increase the temperature. See here also in melting point, heat is being given. It is not that heat is not given, but all that heat is being eaten by the ice because it has to change to water. So the temperature remains. If you measure, it will be constant. The energy is being eaten, but that energy is going where? To convert ice to water. That's why the temperature is remaining constant. Now, okay, at this point at T2, time T2, all of the ice has become what? It has become liquid. And now again I am increasing the temperature. Now the temperature can finally increase. But now it is in which state? It is in liquid state. Okay. It will keep on increasing till one point. Or here, again what will happen? The temperature is going to remain constant because we have arrived at which point? Boiling point. Now the liquid will not directly turn into vapor. Again, thermodynamically, the liquid will also exist, vapor will also exist. They will both be exchanging heat, and more energy I am giving. It is going where? To convert liquid into gas. So the temperature is remaining. Okay. So here T2 temperature is remaining constant. Finally, all the heat is consumed. All the liquid has become gas. Now it can become gas and it will further increase its temperature. Okay. So this is explained in your textbook as well, very nicely. You can read into it, you can understand it. There is also a concept of the slope which is discussed. I have not touched upon this because I don't want to confuse you more. But what I want you to do is, I want you to go through the things before this. Okay. And then I want you to find a relationship between that, and in the textbook it discusses these things, the slope and its whether it's directly proportional to the specific heat capacity and things like that. This thing you can read and you can try to understand, and if you don't understand, in the next class we are going to discuss this. Okay. There is a part in your textbook which talks about it being directly the slope being directly proportional to the latent heat and things like that. Read this. If you read the previous things, you'll understand this thing more clearly. If I tell you now, already the previous thing is half filled in your brain. If you read it properly, you will understand it. We'll discuss it in the next class if possible. Okay, and latent heat actually is the next topic. Okay. So there is something called latent heat or hidden heat. You already know about this now. Do you know about this? You don't know. You actually know, but we have not used this word before. We have understood the meaning, but we have not used the word before. It is called either latent heat or hidden heat. And there is latent heat, I'll just call it LH, okay, of fusion, and latent heat of vaporization. Okay. Latent heat means what, you know? Same thing. If I have some ice and I heat it, it will not directly turn into water. It is consuming some amount of heat before it can turn completely into water. So this is called latent heat. And at this time the temperature will remain constant. Okay, that's all. This is your latent heat of fusion. It's called fusion. Okay. From the quantity of heat which is required to change 1 kg mass from solid to liquid at its melting point. Okay. Amount of heat required to convert 1 kg mass from solid ice to liquid at melting point. So that's why it is even called hidden heat, because you cannot measure the temperature. Heat you are giving, but temperature is remaining constant. That's why it's called hidden heat. Means where it is going, it is consuming, it is eating. Okay, fine. Another one is called latent heat of vaporization. Same thing. You take some liquid, you evaporate it, it will not immediately turn into gas. It will keep taking the heat, and after some time only it will turn into gas. So this is called latent heat of evaporation or vaporization. Okay, and the definition is written like this: the quantity of heat required, it is there in your textbook, you can note it down. If you want, you can write it now. Let's see, we have time. Okay, the quantity of heat which is required to change 1 kg mass of liquid. Okay, you can write it down. Latent heat of fusion you write first. Ananya, you can note it down. Latent heat of fusion. Latent heat of fusion. The quantity of heat required to change 1 kg mass from solid to liquid at its melting point. The quantity of heat required to change 1 kg mass from solid to liquid state, at its melting point. And this definition is there in the textbook also. Okay. Okay. Latent, next one. Okay. Latent heat of vaporization. The quantity of heat, same thing. Okay, heat required to change 1 kg mass from liquid to vapor state at its boiling point. That's all. Okay, now we can talk about one very interesting thing which is called heat transfer. Okay, do you know what are the 3 ways of heat transfer? Any idea? One is called conduction. One is called conduction. Have you heard of this? Have you heard of convection? And the third one, then you should be able to name it radiation. Okay, conduction, convection and radiation. There are 3 ways in which I can transfer heat from one body to another. Okay, so the first one is called conduction. Okay, conduction, in the process of conduction, you can note this down. Okay, in the process of conduction process happens in solid mainly. Okay, mainly it can also happen in other kinds of no, it is solid only. Yeah, but there can also be vibrations which are present in gases and other things. Okay, regardless, fine. So what will happen is, example, I have a metal rod. Here I am going to put one flame. Okay, fire. The fire is heating are here. So there are atoms and molecules which are present, or you can just call it particles that are present inside this, that start gaining energy and they start vibrating. Each of these start vibrating. Understood? Okay. So the thing is, in a solid, no, the particles cannot freely go here and there because they are stuck in their place. Yeah, it is tightly packed. In a liquid, it can move. In a gas, it is even more free. But in a solid, it is tightly packed. So the particles cannot move here and there. So what will happen? The more energy it absorbs, the more strongly it will start vibrating. Okay. So now if the heat has to flow from this point A to point B, how will heat flow? What will happen is, this first row is there, it will strongly start vibrating. Okay. Let's say only the first row is in contact with the, I'll call this row 1. Okay. It is in strongly contact with the flame. Now it is starting vibrating. But the second row is there, no, this second row, it is in contact with the first row. So it will also start getting some of this vibration energy. The third will also is in contact with second one, and it will start vibrating. Eventually, because of this, the highest heat will be here. This will be vibration, second row will be slightly less than the first one, third row will be slightly less than the second one, blah blah blah. It will like this only, the vibration will continue, and it will go up and down, and eventually it will reach point B. Okay. So this process in solid is called conduction. Okay. Here see, process of transfer of heat from one part of the body to another without the movement of particles. Don't write this definition, it is there in your textbook. You can read and you can understand. We'll simply waste time. You have understood the concept, no? If you read, you will understand, no? That's it. Okay. So, all right. Yeah. So, yeah. All right. Okay. So, this is the process which is happening in solids. The second one is called convection. Here what will happen, if I take a pot, okay, and I put some fire here. Let's say I have a gas stove, okay. So this is my fire. Just imagine that this is a very big fire. So what will happen is, this is a liquid inside my pot. First, which one will heat up? Bottom part of the liquid or top part? Bottom. Correct. Because the liquid bottom part is in direct contact with the flame, fire, it will heat up. But now, if the, this one, Charles' law, yeah, I believe it was Charles only. Do you remember Charles' law? Yeah, Charles' law. Remind me. What? Which is directly? What is V? Volume. Okay. So here the temperature at the bottom part, it is increased. Temperature is increased. Okay. So what will increase here? So according to Charles' law, which will increase? Volume will also increase. Volume means what? It is becoming far away from each other. Getting? So now its density has become reduced. Do you understand density, right? Now for example, if I have some water, if I am increasing the volume, like same amount of water I have, I am spreading it everywhere. So its weight will become less. Understand, no? Same amount of water is there, its weight density is increasing, volume is increasing, it is becoming far away from each other. So its weight is becoming less. So if its weight is becoming less, it will go up, and the upper water will come down. Understood? Huh? Upper water, top part of water, down it will heat. This particle will become light in weight. Its volume will increase. It is becoming like balloon. Okay, and if it is volume is increasing, it will go balloon. You know what will happen to balloon? It will go up. So this water will go up, the heated water, and up what is there? Little colder water. It is still not, volume has not increased because temperature has not increased. It's normal. So that water is heavy. It will come down. So next what will happen? Water from down will go up water will come down, and then again now this water is in contact with the flame. Now this will start heating up. So this process is continuing. So eventually all the water will become little hot. Understood? Huh? Okay. So example, if I want to give you again, what is there? I have a flame are here. This is at 100 degrees Celsius. Okay, this is an example. Top water is at 10 degrees Celsius. Bottom it has heated and it has become 30 degrees Celsius. Okay, so this is still hotter. This 30 will go up. What will come down? 10 will come down. Now 10 will increase. It will become 40. What will go up? 40 will go up. 30 will come down. 30 will, now it will become 50. This was what? 40. Up was 40. 50 will go up, 40 will come down. 40 will become 60. Eventually this process will continue till it is all, it cannot be exactly 100, but it will be close to that 100. It is achieved. Okay. This is how our cooking happens. Cooking. Okay. So what is the difference between conduction and this one? Convection. In conduction, particle was not a solid. This is happening in liquid, and it also happens in gas. Okay, because liquid and gas are similar behavior. Okay, but in the first one, the particle was not moving from one place to another. Particle is restricted. It is only vibrating. In the second case, the particle itself is moving up and down. Okay. That is the difference between conduction and convection. Good. The third one is called radiation. Okay. So here the source is also not moving from its place. No problem. Later on you pick it up. The source is also not moving from its place. The receiver is also not moving from its place. Nothing is moving. But the way in which the heat is coming now, it is from something called radiation. The easiest example of radiation is heat which is coming from sun. Okay? It has nothing to do with particle. No particle is involved. Okay, when you are standing in the heat, in the sun, any particle is touching you or what? No. The radiation from the sun is coming to you. It is in the form of light. That light is also carrying heat. Okay. So that is, in this kind of thing, there is something called electromagnetic waves. Just don't think much. Just think radiation is coming. Radiation is coming and it is heating the thing. This is the concept in which you are. Do you have a microwave oven at home? Okay. So, yeah. So, you know what is a microwave oven, right? So, that is how microwave ovens work. No fire is there, nothing. It is going through some electromagnetic radiation. Radiation is given to that, and because of that radiation, it is heating. And it is very fast. It is the fastest way of heating things. You know, if you put an oven in 1 minute, I can heat something up. In fact, in 30 seconds, it will start steaming up something. You know, it is the easiest way. And light is a form of radiation. Just remember that. Okay. So, the properties of radiation are going to be similar to the properties of light. So, what are the properties of light? Light travels in a straight line. correct? Light will always travel in straight line. So radiation travels in straight line. Okay, so it travels with the speed of light. The fastest speed is of light. Okay, so radiation is the same thing. Light is a form of radiation. It travels with the speed of light. So does light need a medium? No, it can even travel in vacuum. In space also it can travel. Same way, radiation can travel in without any medium. Okay, yeah. And does light make the medium brighter? Does it give? No, it does not interact with the medium only. Same way, radiation will not give heat to the medium. It will give only heat to the target or something. It will not heat the medium. Okay, fine. And like light, it will follow the law of reflection and the law of refraction. And there are some properties of light called, do you know, interference, diffraction and all? Yeah, word. Diffraction, yeah, word. Interference, have you heard? Okay. So some of these properties which is shown by light is also shown by radiation, and it obeys something called inverse square law. Yeah, that is currently not necessary. You will understand it much better later on. That is, its intensity basically falls according to square of the distance, something like that. Okay, that's called the inverse square law. Okay, so let's see how much time I have. I have 5 more minutes. Do you want me to cover one more thing, or do you think we can do it in the next class? I'll cover it. Is that okay with you, Ananya? One very small thing. I'll cover it right now.
Yes, sir.
Okay. Hey, but this is the most easiest thing of all. Okay. So when it's talking about radiation, okay, with radiation 3 types of things are possible. Either the radiation will be reflected, or it will be absorbed, or it will be transmitted by a solid. Understood? Okay, fine. Now it is basically talking about interaction of radiation with any kind of solid. What type of interaction is possible? Okay, there are 3 types of interaction. For example, now if you have this radiation, let's say it is light. Okay, now what are the ways in which light can interact with the solid? One is it can reflect. Understood? No, a mirror. Not only mirror, even even your this pouch is reflecting. See the light, can you see it shine? That means it is reflecting. Some at least is reflecting. My ring is reflecting. Okay, whatever it is, some sort of, see, I can see my own reflection. Every material, some amount at least it will reflect. Okay, if it is not reflecting, it may be transmitting. Transmitting means radiation is passing through it. Okay, like for example, our glasses, any transparent medium, what will happen? Light or any radiation may pass through it. That is okay. If it is not reflecting also, and it is not transmitting also, then what is happening? For example, here light is being absorbed. The radiation is being absorbed. Okay, that's all. So if I have, let's say, reflectance, it is defined as, see, reflectance, all these 3 definitions, no, they are very similar. Reflectance, I'll write it by R, okay? Okay, R, reflectance. It is the ratio of amount of thermal energy reflected by a body to it is the ratio of the amount of thermal energy reflected by a body in a given time to the amount of so the term will be amount of energy incident. Okay, means on numerator what will come? Amount of energy which is reflected, down total amount of energy how much I am giving, that's all. Okay, absorbance will be what? The amount which is absorbed. What will be the denominator? Total amount of energy which is given. G incident. Okay, last one is called transmission. Again what? The total amount of energy which is transmitted divided by total amount of energy which is incident, that's all. Okay, it is given by R, A and T. So what will happen is, if I take one object, okay, let's say if I take one wood, the wood is reflecting 20%, let us say, okay, and it is transmitting 0%. Wood is not transmitting, right? Light cannot pass through it, but it is for absorbing 80% of the light. Okay, so if I add R plus T plus A, it will be 100% always. Okay, for any material R plus A plus T is 100. For glass, in some glass I can still see my reflection. No, reflection is quite good, so we can call it at least 30 to 40% reflection. It's quite good. See, I can see my hand and all. This is glass. I can see my hand, no? Reflection is quite good. Let's say transmission is 60%, we can say, but some percent is absorbed. So I'll say 55%. And then how much will be absorbed, man? 5%. So it will R plus A plus T will again be 100 for any material. It will be combination of these three things. Is that clear? In your book it is written as R plus A plus T is equal to 1. Instead of 100%, they take 100 to be equal to 1. 1. So it will all divided by. That's just a way of writing. 0.4 it will be 0.55. This will be 0.05. It will all add up to become 1. That is the easy way to tell. 0 to 1. You will get all your values. That is just one way of telling. Okay, instead of 100%. Okay, Ananya, are you also clear with this? Okay, so with the rest of the things, we will take a look at them in the next class. Is that cool? Okay. Yeah. So can you go home and can you today, guys, can you go through this stuff one time? Yeah. And before 1 minute, before we finish, before we get done with the day, yeah, 1 minute. Before we finish for the day, I want you to do something. Okay. Yeah, I think we'll let it be. We can do this later on only. It's better I handle this. Okay. Okay then. Chalo, bye. We'll be done for the day.